All right, guys, we need to do chapter 6, and we need to talk about the electronic structure of the atom. And we're going to start out here and try to understand waves, because in order to understand electrons, the first thing we have to understand are waves. And so here's what we're going to ask ourselves as we go along. We're going to ask ourselves, what is an electron? We're going to ask ourselves, where are the electrons? And then we're going to ask ourselves, where are they going? And if we can answer these three questions, then we can take and we can truly understand, at least at this level, a little bit of quantum mechanics and a little bit of the electronic structure. All right, we're going to start out here with understanding that light is a wave. So we're going to have to figure out, one, what a wave is, but two, one of the main reasons that we know light is a wave is because of spectroscopy. Spectroscopy is the interaction of light with matter, and we see this from anything from a nice sunburn to an X-ray to even figuring out how much oxygen you have in your blood with one of the little clips that you put on your finger that monitors oxygen saturation. That is all spectroscopy. An MRI is even spectroscopy, and it is a study of an interaction of light with matter. So, to understand electrons, waves is the first start. So, what is a wave? A wave itself is an oscillatory disturbance. What we mean by that is, if you took a string and you imagined that you had a string and you wiggled the string, you could generate a wave. Now, a wave itself has no mass. It is simply taking some sort of medium, whether or not it's a string or even if it's the ocean, and messing with it. And we can put a wave on something. So we have some indicators here that we use with waves. If we are looking at the distance between either peaks or in between valleys, that is the wavelength. The wavelength is symbolized by a Greek letter lambda. The frequency. The frequency would be if you stay at one spot and you watch waves go past. The number of waves that would go past you per second is the frequency. The frequency is symbolized by the Greek letter nu. The higher the frequency, the more waves go past you per time. Now, there are many units for frequency. We can use units of per second. We also call that seconds to the -1, 1 over seconds. We also call that a hertz or an hertz. Anyways, those are all units for frequency. Amplitude is simply the distance between the midline of the wave and either the peak or the trough. It is how big the wave is. All right, we use light in a day-to-day basis for a number of different things. What we call light is in fact visible light. That is this little tiny bit of the electromagnetic spectrum that we can see. So the entire spectrum of light is called the electromagnetic spectrum. It goes from as long a wavelength down here as radio, and you might have a wavelength on the order of about a meter, to as short a wavelength as gamma radiation, which are cosmic rays. And in the middle, we might have something on the order of about 1 nanometer, and that would be ultraviolet. Please remember there are 10 to the -9 meters in a nanometer. We use nanometers very frequently. So if we're looking at around anywhere from about 10 to 400 nanometers, that is in the ultraviolet. If it's shorter than that, down here, it's an X-ray. In the visible, all right, the visible is a portion of the electromagnetic spectrum between about 700 nanometers, the longest, going into 400 nanometers at the shortest. The 400 is about what can get through the lens, and the 700 is about where the retina stops detecting. Shorthand for the visible is Roy B. Biv, and this is red, which is around the 700 nanometer area, and it goes from red, orange, yellow, green, blue, indigo, and violet. Don't ask me what indigo is. I can't really tell indigo from blue and violet. All right, back to the entire electromagnetic spectrum. Note here as we are in gamma, the waves are very, very close together, which means that our wavelength, our lambda, is very short. As we go down here towards the radio, our wavelength, lambda, is much longer. The longer the wavelength, the fewer the waves that pass you per given time. So as the wavelength goes up, the frequency goes down. So here in the short ones, again, as the wavelength goes down, the frequency goes up. Many waves pass you per given time. In here in the middle are all sorts of interesting things. In the infrared are night vision glasses, and you can actually take and see the radiation, black body radiation from human beings in the infrared. In the microwave is anything from our microwave oven to our cell phones. Cell phone towers work here in the microwave in a nice long wavelength, and we love our cell phones, and this truly is an example of light as a wave. All right, well, if we have light and we have waves, and we think about waves as an oscillatory disturbance, and we know that we have some wavelength, which is the distance in between the peaks of the valleys, and we have a frequency. So if we stop and we watch the waves go by, the number of waves that pass is the frequency. And if we take the wavelength, which is a distance, and we multiply it by the frequency, which is per time, we are going to get a speed. If we are looking at light in a vacuum, the speed depends on what we put light through. We're going to round it off and say that the speed of light is 3 times 10 to the 8th meters per second. And our wavelength, or excuse me, our equation is that the speed is equal to the wavelength times the frequency. And we could do some math with it. So let's start and consider wavelength. We want to go from short to long. The short is going to be the wavelength that has the most waves that go past you or the shortest distance between. And we would start with our shortest at gamma. And the next shortest in here would be an ultraviolet. So our gamma is shorter than our ultraviolet. If we look at green and red, we know that we have this Roy G Biv, and this is the shortest. So red here is going to be longer than our green, so our green is next, and then our red. And once we have done all of that, we have a microwave. The frequency, now the longer the wavelength, the lower the frequency, so it is going to be the exact reverse. It is going to be micro. It's going to have a lower frequency than a red, which is lower than green, which is lower than ultraviolet, which is lower than gamma. All right, so let's say that we're listening to the radio as we come into work, and we've got 99.5 megahertz on the dial. By the way, the 99.5, the units on that are megahertz. Remember here that mega is 10 to the 6th. Hertz is units of per second. So our frequency, nu, has a value of 99.5 times 10 to the 6th units of per second. We know our equation is the speed is equal to the wavelength times the frequency. So 3 times 10 to the 8th meters per second is going to equal the wavelength multiplied by 99.5 times 10 to the 6th units of per second. And when we solve for our wavelength, we are going to get a value of 3.02. Now note, our seconds here are going to cancel, and we're going to get units of 3.02 meters. This is in the radio. All right, we can also convert between wavelength and frequency. So again, when we convert between wavelength and frequency, we know we have light. we know that our speed is equal to the wavelength times the frequency. So our speed is 3 times 10 to the 8th meters per second. Our wavelength here is 115 nanometers. So we got to remember what a nano is. We frequently use nano when we talk about light, particularly in the ranges from the visible on to shorter wavelengths. 315 nanometers, we know there are 10 to the minus 9 meters per nanometer, and this is going to give us 1.15 times 10 to the minus 7 meters. So if we have our speed is equal to 1.15 times 10 to the minus 7 units of meters multiplied by the frequency, our frequency is going to work out to be 2.61 times 10 to the 15th. Now, this is meters, meters cancels, and this is going to be per second. And we could either write that as per second, or seconds to the minus 1, or hertz, or Hz. I tend to do it in per second or 1 over second so I can keep track of the units. All right. Now, what we haven't asked is how do we know that light is a wave? Well, the key on knowing that light is a wave is that we have to understand the difference between light versus particles. Light we know is a wave because waves interfere. What does that mean? Well, waves propagate. So let's imagine that we have a wave and it's moving along in this direction. And let's say that we have a wave, and remember the wave is just a disturbance of the material, and we have a wave that is in the same material, and where one is going up, the other one is going down. So let's imagine that we're moving this string or this medium up, and we're moving, come along and we move this medium down at the same time. Well, if something is moving up and down at the same time, the up and the down cancels, and you really get no motion. And our wave is going to just flatten itself out, and that is called destructive interference. Now, if we instead take our medium and we move it up, and then we take and we move it up some more, we grab it, say, from the other end, and we put another wave on this string, and they both are moving up at the same time, we now get really big waves. And this is our constructive interference. Now, particles do not do this. If particles undergo constructive and destructive interference, it would mean that if you take, and you're going to have to forgive my drawing, a car going in one direction and you hit it with a car going in another direction, that instead of having a car accident, you would either take and make 0 cars or you would make great big cars. And we know that doesn't happen. Particles do not undergo constructive and destructive interference. That is only waves, and they interfere.